Good evening. Almost 8 years ago, to be exact, on February 7, 2011, we held the first organic chemistry competition right here in this hall before it was even inaugurated. The organic competition was the first and is the central pillar of the transformative education drive that we started at AUB, with more components branching every year. The mentoring talks component was initiated in 2016 in parallel with the 2016 Makhlouf Haddadin Symposium that was organized on the occasion of AUB's 150th anniversary. Since then, we have been hosting well-renowned individuals to deliver mentoring talks and share with us their life journeys, particularly the problems, challenges, and failures that they faced during their careers. It is truly my distinct pleasure to host Professor Samir Zard for today's mentoring talk. Professor Zard currently holds the positions of Director of Research, Exceptional Class in the CNRS, the French CNRS, Centre National de la Recherche Scientifique, and part-time professor at Ecole Polytechnique. Professor Zard's training as a chemist started right here at AUB, which was interrupted by the Civil War in 1975, then at Imperial College London, and finally at the l'Institut de Chimie des Substances Naturelles à Givry-sur-Yvette, excuse my French, in France, where he received his doctorate under the supervision of Professor Selfdirect Barton in 1983. Professor Zard's main research concerns the study and development of new reactions and processes. He is the author of 357 scientific publications, 38 filed patents, and 2 books. In addition to a long list of academic awards, Professor Zard received the Croix de Chevalier de la Légion d'Honneur in 2007 and the honorary doctorate degree from AUB in 2016. Professor Zard, the floor is yours.
Thank you. Thank you, Bilal. Thank you, Bilal, for kindly introducing me. Thank you for the invitation to come over here to speak before you. It's always an honor and a pleasure to come back to AUB. Like you later, you'll remember that you have many memories associated with this campus. When I went to the United Kingdom, I was talking to Jack Peppercorn, who was running the labs in the university. And I said, oh, this guy, he's funny. And he said, what do you mean funny? Funny, or funny peculiar? The word curious also means the same thing. Is it curious, or curious peculiar? In this case, it's both. So let me try and tell you a little bit about, about myself. So I've structured the lecture in a, well, I don't know exactly how to present this. So I try to structure the lecture in a way to give you a little bit about myself. Then I'll talk about chemistry in general, because I did not know whether the audience would be chemists or not. And then I'll tell you a little bit about our own research. And I'll finish with some observations. So, like almost most of you, I'm a Lebanese, but I was not born in Lebanon. It turns out that my parents got married very early. My mother was 16 when she got married, and my father was 21. And they had to leave Lebanon just after the Second World War to come to Nigeria. So here is Lebanon, here is Nigeria. These were extremely difficult times. My father had left school at 11, so he barely had any schooling, and my mother almost had no schooling at all. They could not speak English, they could not speak the local language, and they had to live without electricity, without running water. My mother tells me that the refrigerator they had was running on kerosene. I've never seen a refrigerator running on kerosene. And of course, Africa is not an easy place to live, especially just after the Second World War. So whatever I can tell you is nothing next to what my parents had to endure in those early days. Here's a picture when I was 1 year old, and you can see my parents wearing the traditional African dress. Of course, my schooling was not done in Africa. I came and became a border school at the Collège des Frères Maristes in Jounier, which later became Chanville. So I was a border student. But when I was 11, my mother came for Christmas, and she took me with her to a toy shop because she wanted to buy toys for my brothers and for my cousins. And I was a quiet one in the family, and I would help her carry the stuff. So we went to a toy shop, which is Sehet al-Nijmi. It does not exist, unfortunately, anymore. And we went into the shop, and my mother started looking for toys for my cousins and my brothers, and she said, go and find something for you. So I went around, looking around the shop, and I would go, and then I saw this box, which had stuff which looked like salt, which had crystals, and it was very, very curious. So I would go and then come back to this box. And there were blue crystals of copper sulfate. Of course, I did not know at the time they were copper sulfate. And it intrigued me. And I said, Mom, I would like to have this toy for me. And I got hooked. I think copper sulfate has done more for chemistry than all the professors of chemistry, because this attracted people to chemistry, these beautiful crystals. And I got hooked. And little by little, I started increasing my stock of chemicals, and I built my own little lab next to the kitchen, my mother's kitchen. So this is, I was 16 then. And what's interesting is I had this cat, and this cat had the habit of playing in the garden, and I would leave the window open a little bit, and so it would jump on the windowsill, and then jump on the table, and then come and eat. And I prepared one day some nitrogen triiodide, and I put it to dry just under the window, and I forgot about the cat. Now, nitrogen triiodide, when it's dry, explodes even if you touch it with a feather. And the cat, so I had it on a filter paper, and the cat came here, jumped onto the window, and then jumped bang onto the nitrogen triiodide, and the thing exploded under its feet. It's not a very dangerous chemical. It makes a big bang, but it's not a very powerful explosive. And the cat jumped in the air, went out of the window, and disappeared for about 3 days. And only came back when hunger overcame its fear. And it came back, and so it was a funny thing. The other experiment I did, which was very, I did many experiments, is to prepare bromine in a retort. Now, this doesn't look impressive, but a retort is something like this, and bromine boils at 60. So you put the stuff in here, and then the bromine comes and condenses here. But something that boils at 60 with such a poor cooling system, it comes as vapors, and you start sniffing it, and I started coughing because it's not very good for you, and I got scared. And so I didn't know what to do. And fortunately, I had an old pharmacopoeia. So I went in and looked into this pharmacopoeia under bromine, and it was said antidote, ammonia. So I went and took the bottle of ammonia, and I started smelling ammonia. It was worse than the bromine. I never repeated this experiment, I can assure you. What also happened at the same year was that in the summer, Professor Suhail Bashroui, who was professor of English at AUB, who was a friend of our family, he knew about my chemical passion, and he arranged for me to come as an auditor to AUB. And so I came and attended Chemistry 101, given by Professor Sarkis. Professor Sarkis, I can still remember him until now. He was a towering figure with a voice which was a stentorian voice and very intimidating. And this allowed me access to the labs in the chemistry department, so I saw what a real lab looked like. And also it gave me access to the fantastic Yafet library. One of the problems I had at the time was how to get my hands on information, on books on chemistry. In bookshops, you hardly found any chemistry books. But by having access to the Yafet library, I could go up into the stacks and just look at all the chemistry books. It was like, you know, Wonderland. And my eye fell on this book here. And so I would borrow this book, and every 2 weeks come and renew the book. And I borrowed it for almost a year until I got my own, more than that, for 2 years, until I got my own copy. I managed to get my own copy. And I repeated, I've done most of the experiments in this book. Anything I could do where I could get the chemicals, I did that. And one of the compounds I made in the same room that you see here is potassium O-ethyl xanthate, which is very easy to make. I'm mentioning this because I did not know that later in my life I would publish more than 200 papers on the chemistry of xanthates. I'll tell you about this a little later. Okay, now we have done many things, but I had an accomplice, a long-time friend, Tony Atiye, and we have done so many mischiefs and pranks that if I listed them, we would be expelled from this country immediately. Explosives, whatever you think of it, we have done. Here is a picture of us in our aura, and this guy you see with the disheveled hair and looking like a hippie is the professor you see in front of you today. Okay, so you can see that, you know, you change a lot with life. Okay, then when I was 18, I was admitted to AUB, and I was very fortunate that it happened, and of course I was very interested in organic chemistry. And in my time, it was Professor Kostas Isidoridis who gave the chemistry to 11 to 12. But of course, I had heard of Professor Haddadin, and I would sneak to the back of the lecture room to listen to his lectures on the same course, and to compare the two, and to have the different views on the same subject. So again, I was very fortunate to have these exceptionally gifted teachers. Unfortunately, I had to leave in 1975, one semester before I graduated, because I could not come to the university, and the university eventually closed for a while because the Civil War started. And so I had to leave. But let me say before I do that at AUB I also made a very good friend, Dr. Tariq Mansour, a wonderful person and a superb chemist. So we were together in the chemistry department, and he went to Manchester, and then to the United States, and then to Canada, and back to the United States. And we still see each other quite frequently. In my case, first I went to France, and they would not take me because they would not accept the grades I had at AUB. And they said, no, you have to start from scratch. I said, look, I've been in the university for 2 years. You cannot, get me to start from scratch. But unfortunately, they would not listen. So I went to the United Kingdom. And first I tried to get into King's College, and they wouldn't take me. And then I managed to get an interview at Imperial College, and they made me pass an exam. First an interview, then an exam, and I passed, I presume, because they gave me a position immediately. This was in January 1976, which was the middle of the session. The students had already been at the university for 4 months. But nevertheless, they took me in, and this was the most fortunate thing that happened to me. So in a sense, the civil war in Lebanon was a blessing for me in terms of my profession. I'm not talking about, of course, all the tragedies that came with it. Because I had the very great fortune to meet this great man. I did not meet him as an undergraduate. He gave 4 lectures. So he never spoke to the students. But in my third year level, I stayed only 2 years at Imperial College. His secretary came down to the lab and said, Professor Barton would like to see you. And I was scared like hell. I went shaking, and it took only 30 seconds. He said, I'm going to France. I've been appointed director of the Institut de Chimie des Substances Naturelles. Would you like to come and do a PhD with me? And he said, I'll be away today. Give your answer to my secretary this afternoon. Thank you very much. And I went out and I didn't know what to do. And of course, I immediately said, I'm going to go to France. And so here is a letter that I received shortly afterwards, January 6, 1978. And then he said, to confirm that we should be very glad to have you here. And then he says that I'll be working with Dr. Motherwell on some aspects of creative organic synthesis. And he can offer me 3,000 francs per month, and so on. And a very nice letter, very, very kind. And so I went to France, and for the first month, I lived in a chateau. So this is 17th century chateau, which is in the park in Gif-sur-Yvette, and I was here up for 1 month. The park is beautiful. It was September, so fortunately we had lovely weather, and it was very cheap. I only paid 12.5 francs per day. Nowadays money, it's less than $10 per day for a room in a 17th century chateau. That was very good. Unfortunately, I could not stay for more than 1 month, and then I had to leave. It happened that September 1978, Professor Barton was born on the 8th of September, so it was his 60th birthday. And he had this party in his flat, and he invited everybody. I knew nobody. It was only a week I've been in there. And so I was standing there, by myself, with a glass of orange juice, and all of a sudden I saw him coming to me. And he said, "Mr. Zard?" I said, "Yeah." He said, "Are you settling okay?" I said, "Yes, sir." And then he said, "Do you like cheese?" I said, "Yes, sir." He said, "What kind of cheese?" I said, "Gouda, Emmental." He looked at me in disgust. He said, "This is not cheese. This is mousetrap cheese. Real cheese jumps in your stomach." And then he turned and went away. And I said, "God, I've been here only for 1 week and I flunked it." Fortunately, it turned out better than that. Here is Professor Motherwell, who was the intermediary between Professor Barton and myself and the other people in the lab. And I immediately hit it well with Willie. He is an incredibly nice person and, of course, a superb chemist. So I was very fortunate to have 2 people looking after me. And we are still very good friends. I mean, it's been a long time. Here we are with Willie. He has been very influential. He has had a strong influence on my training as a chemist. Okay, here is Professor Barton and his group. This is his big office in France. Here is Willie, and I'm standing here. Here his secretary is Su Chen Fan, a very wonderful lady too. I also had the chance to meet Pierre Potier. Pierre Potier is I did not have much scientific interaction with him because he had another group. But for some reason, he took me under his wing and he protected me over many, many years. And he saved me from many nasty colleagues, I can assure you that, and administrators. He's also an extremely nice person, and I will always be grateful to him. What's interesting about Pierre Potier is he had a fantastic sense of humor. One day I bumped into him in the stairs, and he said, "Oh, how are you doing?" I said, "Okay, we just found a reaction by accident. Serendipity." I was trying to impress him with this word, serendipity. He said, "Oh, serendipity, serendipity. You know what's the French definition of serendipity?" I said, "No." He said, "Yes. Serendipity is looking for a needle in a haystack and finding the farmer's daughter." So this is the French macho definition of serendipity. Again, a very great person. Just to give you an idea, he's the one who found Taxotere. In fact, he found 2 drugs against cancer, Nevelbine and Taxotere. And Taxotere brought at least 400 million euros to the CNRS. This patent was more, and the Nevelbine patent brought in more than 90% of all the royalties to the CNRS. Okay, so let me now just tell you a little bit about chemistry in general, and then I'll tell you about our own work. You see, there is a Hindu legend that says the earth is standing on the shoulders of an elephant, and the elephant is standing on the shoulder on a turtle. And then if you say, "I'm the turtle," they say, "Oh, let's change the subject." In science, it's about the same thing. biology rests on the shoulders of chemistry, and chemistry rests on the shoulders of physics, and physics rests on the shoulders of mathematics, and mathematics is on nothing. In fact, of course, I'm joking, but mathematics does not have to conform to reality. As long as you have a coherent system, it's okay. But physics and chemistry and biology have to conform to nature. And of course, there is no boundaries between them. These are artificial boundaries. Between chemistry and physics, you have theoretical chemistry, you have material sciences. Between biology and chemistry, you have molecular biology, biochemistry, enzymology, etc., etc. So it's a kind of continuum, and each feeding off the other and improving and expanding. But chemistry has a special position in the sense that it's a science that also feeds the other sciences, because it's the only science where you can modify material. You can take matter and modify it and convert one compound into another. So here is a citation from Darcy Thompson, who said chemistry is the most cosmopolitan of sciences and the most secret of arts. Let me show you how it is the most cosmopolitan of sciences. Here is a building, if you visit London, you'll probably have a chance to see. It's a strange building, it's called the Gherkin. It's a Swiss bank, in fact, I think it belongs to a Swiss bank, but it's not what I wanted to show you. This is the building I wanted to show you. It's a cathedral, a small cathedral next to this building. You see, the architect who imagined this cathedral could have very well imagined this building here, but he couldn't have built it because he didn't have the material. Here they were stuck with poor quality concrete. They couldn't go very high, poor quality steel. They had no real steel. The windows were small. They couldn't make big glass panes. They had problems with leakage, with insulation, and so on. To build this, now you have silicon joints, you have self-cleaning window panes, you have steel of high quality, concrete of superb quality, and so on and so on. I'm mentioning this because if you think about it, chemistry is also like a construction game. You imagine things, you imagine structures like an architect, and then you build them. In this case, you have to use concrete slabs of stone and what have you. In chemistry, you have this periodic table. Ourselves and everything around us is made from these elements. A little bit over 100 elements, and the chemist is able to put them together. And depending on how you do it, you get different stuff. And let me show you the influence of this, the ability to change matter. Here is a picture of a Norwegian ski champion who, in the first Olympics, he won essentially all the medals. But look at his accoutrement. Look at his shoes, look at his clothing. Just wool. Look at his ski sticks, bamboo. 1924, they had to use bamboo. Of course, things get better if you go to 1935. Now you have aluminum ski batons. Look at the size of the camera. I don't think many of you have seen such cameras, except in museums. This is a modern skier. This is Alberto Tomba, Tomba la Bomba. He has Kevlar protection, carbon fiber ski batons, and he has Gore-Tex outfit, and special glasses for sun to protect him from the sunshine, and so on and so on. And this is nothing next to a spacesuit. A spacesuit is made of something like 30 layers. It cost over $10 million. And each layer is made of special material made by a chemist, because an astronaut has to survive in high vacuum, high temperatures, very low temperatures. Without this protection, he cannot survive. And it tells you how chemistry has advanced and allows now such explorations. Of course, in everyday life, you have these gadgets, and chemistry is in every part of them, from the display, from the casing, from everything you can see. And also in the inside, because these microchips, this is the finger, so this is a tiny microchip. You require at least 1,000 different chemicals to make a microchip. Without chemistry, no microchips, no telephones, no iPads, no iPhones. But in fact, everything you see, if you go to a supermarket, everything you see in a supermarket has been touched at some point or another by chemistry. If you remove chemistry from a supermarket, that's what you get. And in fact, it's worse. And it's even worse. That's what you get. People will be naked in trees. You think I'm joking? There aren't enough, if you remove chemistry, there won't be enough fibers to clothe everybody. In fact, the American Civil War was in part due to the demand by Europe of the for cotton. And of course it was growing, the best place to grow cotton was in the southern part of the United States. And so the people there were becoming rich with the cotton plantations. And they did not want to relinquish this advantage of having slaves working in the cotton fields. And he wouldn't be so clean. Let me convince you that this is the case. This is a citation from Henri Monnier. Of course, this is the original French citation, but he says, London is a city of mist and charcoal. After 8 days, a shirt is no longer wearable. Because people at the time, did you ever try to put a shirt for 2 weeks? Your mother will kill you. At the time, putting a shirt for 2 weeks was common because people had only maybe 2 shirts, one for special occasions, maybe Sunday Mass, and a shirt for every day. In fact, I learned that in the United Kingdom, in the 19th century, if you stole a shirt, it was 6 months in prison because shirts were very precious. And as I said, you know, the guy wouldn't be so clean because all the detergents, shampoos, are made by chemistry. All of the stuff that you see is made by chemistry. Let's go to something more serious. This is again a citation by a philosopher, Thomas Hobbes, The Life of Man, Solitary, Poor, Nasty, Brutish, and Short. Let me show you how short it is. It was. This is Edmund Halley of the Halley's Comet, who was in fact also a statistician, and he went to the city which at the time was in Germany, now is in Poland, Breslau, and he did some studies on the records they had. So this was 1693, at the end of the 17th century. And he found that for every 100 births, after the 10 years, half of the kids were dead, 50% before the age 10. And only 3 people out of 100, I mean 3 people out of 100 who were born arrived to the age 80. Now the trend is completely the opposite. Most people, and your generation, most of you will hopefully be centenary, you know, will live for 100 years. Here are some famous people. I'll not go through the whole list, but when you think about it, Mozart was dead at 35 from a fever. Schubert was dead at 31 from typhoid fever. Schumann was again dead at 39 from tuberculosis. Schumann, let me see, from syphilis. Not many, I don't think you know anybody who died from syphilis or who has syphilis. But at the time it was decimating many, many people. Even George Orwell, who lived in the first half of the 20th century, died of tuberculosis. This is terrible. Emily Bronte and her sisters, look, they lived only 22 for Emily Bronte. From tuberculosis, she died from tuberculosis. This here is a graph for the life expectancy in Japan. Something again people don't realize. In Western Europe and in Japan, the average life expectancy at the beginning of the 20th century was just over 40 years. And it only improved slightly until 1950. It went to about 45, let's say just under 50, maybe 48. And then all of a sudden, a big jump. And in just a few years, 20 years were gained in life expectancy. This is due to penicillin. which the American and the British introduced after the Second World War. One molecule made a huge difference in life expectancy. I'll come back to this a little later. In fact, all the drugs that you find in a pharmacy are made by chemists. And even the package and the ink is made by the chemist. Here is a citation also, which is something people don't realize. This is the original French by Anatole France, and it says, Holy Mother of God, you who conceived without sin, grant me the grace to sin without conceiving. Contraception was a big problem. People didn't know how to do it. Of course, it looks a little bit, maybe funny, but women who married early, like 14, 15, 16, could not stop getting pregnant. And by the age 35, they had maybe 10, 15 pregnancies. Well, maybe not 15, but maybe 10, 12 pregnancies. And their bodies were completely wasted. This is a big problem. Now, the British had found a partial solution, which I'm showing on the next slide. But this is not a general solution. Fortunately, chemists have come up with a more humane and better solution to contraception. Let me now go to the second part of the citation of Darcy Thompson. Chemistry is also the most secret of arts. If you tell your mother-in-law, Madam, would you like some beta-D-fructofuranosyl, alpha-D-glucopyranoside in your coffee? She would think you are trying to poison her. In fact, this is nothing more than the sugar you had in your coffee this afternoon. It's just that chemists have to give names to structures. There are an infinite number of structures. And so for those of you who are not chemists, I'll just go through this very quickly. So for example, if you have something like this, which is CH3, CH2OH, it's just ethanol, it's the alcohol in wine. You can write it like this, you can write it like this. And of course, this is cumbersome, this is less cumbersome. And this is one of the simplest ways to write ethanol. It's so common that you can now write it like this. And ethyl stands for ethyl. Chemists have to describe the structure to other chemists, and so they have to use this jargon, which for non-chemists sounds like, I don't want to say Chinese, but incomprehensible. And of course, so you have things like cyclohexane, just says it's a cycle with 6 carbons, and it's saturated, it's hexane, it's unsaturated. And you see, if you draw it like this, you put all the carbons and hydrogens, it takes you time to draw it. So chemists have come up with this simplified way to draw it. So every time you have a corner here, you have to complete the 4 valencies of carbon. So you see here there are 2 bonds, so you have to complete with 2 CH bonds. And so this is a very simplified structure, and this is a much better way to draw things. So you have to draw structures which look strange to people, and you have to name them with funny names, which again are incomprehensible to non-chemists. This again is the structure, so this is just telling you that there is a fructose attached to a glucose in a certain way. Okay, this now becomes, and of course it can sometimes take half a page, the naming, and even chemists cannot come back with this, come back to the structure. Here's the structure of penicillin, and now penicillin is not good enough because bacteria have learned how to deactivate it. And so chemists have to combat bacteria and try to be one step ahead by making penicillins and other antibiotics which are more and more efficient. A huge amount of work is involved in this. Here's another molecule I'll show you. This doesn't say anything to you, FK506. This molecule has revolutionized the grafting of organs. It's a miracle drug, and I've seen it in person, in the sense that my cousin had a daughter who has now the same age as my daughter. When she was born, she had her liver had a problem, and she was going to die if she did not have a liver transplant. So she came to France, and she had 2 liver transplants, because the first one did not succeed. The second one fortunately succeeded. And she's now treated continuously with this, because this is an immunosuppressant. It diminishes the rejection of the organ. And now she's still alive. She got married. Every time I think of her or I see her mother, I've not seen her for a long time. but because now she is in Japan, it's a miracle. It's just a miracle. She should have died 32 years ago. She's still alive. This is an artificial heart, which is made again by an alliance with chemists and physicists, between chemists and physicists. Of course, drugs is not just chemistry work, it's an alliance between biologists, medical doctors, and chemists. Okay. Let me now just leave drugs for an instance. How about dyes? Dyes for your clothing. If you look at the pictures of and the paintings of all the armies in the past, the dominant colors were red and blue. These are Polytechnique students, and their uniform has this red band here, which is made from alizarin, which is colored by alizarin, which is extracted from the madder plant, and indigo, which is the dark blue, which comes from the indigo plant. You never see the royal purple for soldiers, because this was extremely expensive. So this is called the royal Tyrian purple, and it's extracted from a mollusk, and it takes 12,000 mollusks to give you 1.5 grams. You can see how expensive this was. In fact, only kings and emperors could have this kind of, yet the difference is only 2 bromines. It's the same structure as indigo, except that you have 2 bromines. The thing is that bromine, you don't find bromine on land, because all the bromine salts, or very little, but all the bromine salts are washed to the sea. So brominated natural products are essentially only in sea animals. And in the Roman times, the rich people could not even pay for a whole, dyeing the whole uniform, I mean the whole clothing or tunic. And depending on how rich you are, the band that was colored in purple was wider. So the wider the band, the more, the richer you were and the higher status you are. Now with chemistry, any idiot, excuse me the term, can have as many colors as they like. You can have this, you can have any color of the rainbow. I wouldn't want to have a fight with the lady who wears this underwear. She'll beat the hell out of me, I think. Okay. Something else about chemistry. This here is glucose. It's easily extracted and made on an industrial scale. 1 kilogram costs about €1, $1. This molecule here is this molecule here, which you see. It's called discodermolide. It was almost became an anti-cancer. It's an anti-cancer compound, but unfortunately didn't make it to become a drug. And this 1 gram, not 1 kilogram, 1 gram, it took several years to make. And this 1 gram costs about the equivalent of maybe 2 apartments in central Beirut. Now, if you put this on the table, nobody would have any qualms about just kicking it over and throwing it in the rubbish bin. Because a non-chemist had no idea that how expensive this could be, or how complex it is to make such a powder. They all just look like 2 powders. And this is something chemists have a problem with, how to convey the complexity of structures and how difficult it is sometimes to make compounds. It's not just mixing, and it's complex. Okay, let me touch on something that sometimes also puzzles people. For chemists, I mean, it should be obvious that the function of the properties of a compound depend only on the structure. They don't depend on who made the compound. So people think that synthetic compounds are different from natural products, and that for some reason synthetic compounds are bad for you and natural products are good for you. This is vanillin you have in your ice cream or cakes or what have you. If you extract the natural vanillin, determine the structure, it's exactly the same as the synthetic vanillin. The difference, of course, is the price. This one tends to be much more expensive, but it's exactly the same. People have this confusion about synthetic and natural. All of us are doing chemistry all the time. Your body is doing chemistry all the time. It's converting matter. When you go to the kitchen and you cook something, you heat, you boil an egg, you're doing chemistry. Why does the egg become hard? You've created sulfur-sulfur bond between the thiols in the proteins, and the proteins become solid. This is chemistry. When you drive your car or light a cigarette, you're converting matter. You're doing chemistry. It's just that we try, as a chemist, we try to do chemistry in a controlled manner by starting with one compound and converting it into another compound. When you make a cake, you are converting thousands of compounds from one to the other. Natural compounds are not necessarily good for you. Here are 3 compounds I wouldn't give even to my mother-in-law, especially not to my mother-in-law. I love my mother-in-law. She passed away, unfortunately, 6 months ago. But she lived until 99, which was almost unheard of a century ago. This is strychnine, comes from a tree in South America. Extremely toxic, extremely bitter. Tetrodotoxin is the toxin that you find in the fugu fish, which the Southeast Asian people, Japanese especially, they like. It's very expensive and they like very much. But the cook has to remove the toxic parts. Nevertheless, every year a few people die because they ingest a little bit too much of this tetrodotoxin. Aflatoxin is one of the most cancer-causing drugs and compounds you can ever have. And these are natural products. They grow on peanuts sometimes. You know, it's a fungus that sometimes grows on peanuts. Extremely dangerous compound. And they are natural. Again, it does not matter who made the compound, whether it's nature or a human being. It depends on the structure. Let me finish by saying a word about DDT. Look what happened in Ceylon, or Sri Lanka, now formerly Ceylon. At the time, the population was about, so in 1960, the population was 10 million. Nowadays, it's 22 million inhabitants. In 1946, they counted nearly 3 million cases of malaria. That was before the start of spraying DDT. 8 years later, it went down from 3 million to 150. And then they decided that DDT is bad for the environment. And they stopped spraying DDT. 4 years later, they went to nearly 500,000 cases. And 6 years later, it went to 1.5 million cases of malaria. If you know that malaria killed more American soldiers than the Japanese bullets, how many of these died? DDT has probably saved more lives than all the antibiotics put together. Unfortunately, they stopped spraying DDT too soon and caused the death of many, many million people. This was not done on purpose, of course, but this was done on the basis of some not correct assessment of the situation by bureaucrats who were not living in these countries. I mean, this is just Sri Lanka. Think about India, South Africa, South America, the whole of Africa. This is a terrible decision. Maybe I can draw, in real life, you will find that there is never a perfect solution. And in your life, you will often be confronted with a situation where you have an imperfect solution. And then what do you decide? You have to put things in the balance. What are the drawbacks? What are the advantages? And you make a decision. And you hope that with time you get a better solution. And then you move to the better solution. In this case, they stopped the imperfect solution without having a good solution. And so they caused a lot of damage. This is, I think, a kind of lesson that one should take from situations like these. Yeah, that's a tragedy. Okay, let me now finish by showing you a little bit of our chemistry. So, as I said, chemistry, you can see chemistry like this. You have starting material, and you convert it into a product. By some process, by heating, by cooking, by mixing with other reagents and so on, you convert matter. But to be able to do it in a controlled way, you have to be able to understand reactivity and reaction mechanisms. And of course, this understanding allows you to invent new reactions, and this would improve your understanding of reaction mechanisms. So you have a give and take here, back and forth, you know. And so you think of a reaction as a tool that allows you to convert starting material into product. And the product hopefully will have an interesting property that you will want to use. It could be a plastic, it could be a glue, it could be a coloring matter, it could be a drug, it could be a detergent, what have you. Or it could be just for fun. So, as I said, I was fortunate to meet Selfdirect Barton, and I tried to follow his teaching. And so he had an enormous influence on the way I do chemistry. And so, as you can see here, he said, you know, if you know how to do a reaction, you should not do it. So try and find a new reaction. And I also, you know, with my reading, I tried to adapt to myself. So here is something from Sir Peter Medawar. You can see from his name that he's of Lebanese descent. He was born in Brazil, and he got the Nobel Prize in 1965. Superb scientist and superb writer of English. But he said, I mean, I adapted what he said. And so there is a French saying that the definition of a problem is already half the solution. In scientific research, the difficulty is often finding a good problem. That is a problem that can be solved with the intellectual, technical, and human means at hand, and whose solution is not only sufficiently important to warrant the effort, but also leads to consequences and ramifications that go well beyond the problem itself. So we have tried to apply this as much as we could. So let me show you a few problems, and I will stop. I'm sorry, I will complete that with some observations. One of the problems we had was to synthesize things like cortisone. And so these are very important drugs. You hear cortisone, people have heard of. Cortisol is just the reduced form here. And these are more elaborate derivatives. And the problem we had was the following. It turns out that people had found a way to take something like cholesterol. So this is the structure of cholesterol. And they found microbes or microorganisms which were modified in such a way that they were able to eat the side chain here, the whole thing in the top there, and modify a little bit this part. And they were able to convert cholesterol and cytosterol, which is very abundant, is found in soybean, for example, and they could eat the side chain. And depending on what microbes you used, you could get either this molecule or this molecule. So these became very interesting starting materials for the industrial synthesis of corticosteroids. So the problem for us was how to reconstruct the side chain. This is the cortisone side chain. How to build it starting from 17 ketones. Now this position here, of course a chemist would immediately see it, but it's a hindered position, which means that this, what is called a ketone, is not very reactive. And our approach was to try and find a way to condense nitromethane with this ketone. With simple ketones, this was a known reaction, but it was not known on a hindered ketone like this. So how do you go about solving this problem? We figured out a solution, and that is to use a very simple molecule, which is this one, a diamine. You put 1%, and you are able to catalyze the condensation from here to here. This hinges on one principle, and that is if two people don't like each other and you want to force them to talk to each other, you lock them in a small room and they have no choice. They have to talk to each other. And this is what this little molecule does. You see, one end of the amine condenses with the ketone. You lose a molecule of water and you make what is called an imine. But you still have this basic amine. Now this is capable of deprotonating partially nitromethane to give you now an internal salt. You write it like this, but this is the more likely structure where this hydrogen here is between the two nitrogens, which means that you transfer a little bit of the positive charge from here, from this nitrogen to this nitrogen. And so electrostatically, by electrostatic attraction, the negatively charged nitronate is attracted to the positively charged nitrogen and finds itself in very close proximity. And now there is no choice. It attacks. You get this intermediate, and then, of course, you deprotonate, eliminate, recover your catalyst, and you do this condensation. And so this now becomes a very good way to do this kind of condensations, and it solved the problem of the construction of the corticosteroid side chain. Now, my love for the chemistry of nitro compounds then became, it translated into another reaction where you condense an isocyanide with such molecules here, and even can be extended to what are called sulfones, and this condensation produces a pyrrole, and it has turned out to be a very powerful way to make pyrroles, and it's called the Barton-Zard reaction. And it's a textbook reaction now. It's perhaps the most powerful way to make pyrroles. But it should be really called the Shulkov-Barton-Zard because it's based on chemistry devised by Shulkov before us. So I think this should be corrected at some point. Nevertheless, why are pyrroles important? Because they are the building blocks for very important molecules. Chlorophyll. Chlorophyll, without chlorophyll, no photosynthesis. No photosynthesis, no life. At least no mammals, no human beings. So you can see here 4 units of, which have been modified more or less. Hemoglobin, no oxygen fixation, no respiration, no life. Vitamin B12, very complex structure, beautiful structure. Here you can see cobalt in the middle, magnesium here, and iron here. And these are approximately the colors. Vitamin B12 has a beautiful purple color that you can see here. Here is another reaction which we worked on. Now this reaction was not discovered by us. It was discovered by serendipity, by accident, by Sharon Abidi, who was working in the Fish and Forestry Department in the United States. And this is an incredible reaction because you take an alkene which has 2 substituents here, 2 methyl groups. Methyl is CH3, okay, CH3, CH3. And somehow you lose the equivalent of methane and you get an acetylene. This is incredible. I mean, for a chemist, this is almost impossible. But this reaction was reproduced, but not the yields. So E.J. Corey and his group at Harvard, they studied the reaction. They could not reproduce the yields of Abidi, but they reproduced the reaction. So this is not, I mean, it's a true reaction, even though the yields are very poor. But E.J. Corey proposed the mechanism, which Sharon Abidi did not. But they found, again, you see this nitro group here, and they found that this was the first intermediate. So this is converted into this, which could be isolated, and this could be converted into the acetylene. And they proposed the mechanism that goes from here to here. So this is essentially speculation, with some experiments. But there was a step which was difficult, which is this one. And so when I first saw the Abidi reaction, I could not write a mechanism for this. But then I saw the paper by Corey and his students, and I saw the nitro compound, and I thought maybe this part should be amended. And maybe we could find a way to go from here, jump over, go to here, and avoid this difficult step. Or maybe propose a completely different pathway. And this is what we did. We proposed a different pathway. I'm not bothering you with details. Okay, these are technical details. But maybe the next intermediate is this green one here. And indeed, we showed that you could go from this green intermediate to acetylenes under the same conditions. And then you can write these intermediates. Of course, this is fun. But in terms of practicality, it's a very poor reaction because the yields of acetylenes were not good. But we thought about this last intermediate here, and we said maybe if we could find a way where we could very quickly get to this intermediate, then we can avoid all these difficult steps and maybe have a good synthesis of acetylenes. And so you're guided, you see, by errors, and so on, by things that don't work. And we figured out a way that you start from a very simple structure using, again, a very easily available reagent. You do a condensation. This gives you a structure like this, which you can write like this or like this. And if you nitrosate, you get a structure like this, which fragments, and you get a structure like this. And you can see this is very similar to the previous one. And now you can lose CO2 and N2O and make an acetylene. So you see, essentially, you go from here to here very quickly. And this now becomes a much simpler and much more useful synthesis of acetylenes. And this is indeed the case, because now you can see that you can take a structure like this, cut it and make acetylenes. We had to tweak the mechanism because the first experiments we did failed because there was a pathway which we did not anticipate, and we had to correct by adding iron sulfate. And so now we could make acetylenes. Here's an example, here's another example. You can make cyclic acetylenes, for example, which are also very useful. And so, you know, as you do in science, once you essentially complete the kind, or at least complete the stage of your work, you write a review. So I wrote a review telling the story of this thing here. And so this was in 2002, and as soon as the paper appeared, maybe a couple of weeks later, I was surprised to get an email from Professor John Cornforth. Now, Professor John Cornforth is a Nobel Prize in chemistry. He got it in 1975. And he's a fantastic chemist. And he's one of my heroes. He's one of my heroes. And getting an email from John Crawford was like getting an email from God. And of course, it was a very kind email. And he said, he congratulated us on the nice work. And then he had a tremendous sense of humor. He said, I have often thought that the devil only invented sulfur chemistry because he found nitrization chemistry too difficult. Now, so this was, I can tell you I was very happy the day I received this message. Here is a picture of John Cornforth when he was younger. He was deaf. He became deaf when he was young, maybe 10 or 11. His nickname in the chemistry community is Kappa, because he was initially trained as a classicist, so he could speak fluently Greek and Latin. He still, I think, until now holds the record in Australia for the number of chess games played simultaneously and blindfoldedly. So he was blindfolded, I think it's 12 games, and I think he won most of them. This is absolutely incredible. He is a fantastic person. And as I said, he had a fantastic sense of humor, because when Sir Derek Barton moved to France, Sir John Cornforth sent him this limerick. Imagine Sir Derek de Barton consuming French girls by the carton, dismissing each wench in impeccable French, c'est fini, rabis-toi et va-t'en. Very, very interesting. As I said, this work was started by Corey, who figured out at least the key aspect of the mechanism. And so we interacted with E.J. Corey. And as you can see from his name, he also comes from Lebanon. His mother comes from Aoura. And we were very fortunate to be invited to his home in 2014. And we correspond with him regularly. And I did not know that, but he is a very keen cook. You see, chemistry is not just in the lab, it's also in the kitchen. And so he cooked a very nice meal for my wife and I. And we spent a very nice evening in his. You see, that's one of the things about science. You see, when I was an undergraduate, these were heroes. Woodward, Corey, and all these were here. We'd see their names in the books. And never I would have imagined that I would have a chance to visit him and talk to him and discuss chemistry with him and many other things besides chemistry. Okay, the last thing I will tell you about is this. Again, I'll go very quickly. The most important thing that we have managed to achieve is finding a solution to this long-standing problem in organic chemistry. How do you create a carbon-carbon bond on a simple alkene which has no activation? So it's a lazy group, does not want to react. Now, it was very well known that you could do intramolecular reactions, again, because they are in the small room and they have no choice but to fight with each other. So here, this is easy. This was difficult, and there were very few reactions which allowed you to do this in a fairly general way. And we came to this problem by accident again. You see, Barton and Maccombie, one of his postdocs, found this reaction which allowed you to remove a hydroxy group, an OH, from a complex molecule and replace it with a hydrogen. And this went through what is called, again, xanthate. So this functional group here, the xanthate, and you can see it could be done on very complicated molecules. Even now, this is still the most powerful method for removing, replacing an OH with a hydrogen, and various other groups, but mostly with hydrogen. The thing is that the mechanism, I will not go through this, but initially Barton and Maccombie proposed that the tin radicals, the radicals centered on tin, would attack this sulfur. And then Atul Beckwith, who was a former Barton postdoc, who was an Australian, proposed on the basis of some ESR experiments that maybe there is another mechanism which went through attack on this sulfur. Now, Atul Beckwith and Sir Derek were very good friends, of course, and they liked to fight with each other, I mean, tease each other. And I became very good friends with Atul Beckwith. He was a wonderful person. You know, like the Australians, you know, easygoing, straightforward, wonderful, wonderful chemist too. When he passed away because of an accident, I was extremely sad. He's a very, very nice man. He was, sorry, a very nice man. Okay, and so this led to a series of experiments, and we thought maybe we could gain something by switching the groups. You see, the group you're interested in is on the oxygen in the Barton-McCombie reaction. We put this on the sulfur, and now things became completely different. Because now you could take this xanthate, the R group is on the sulfur. You put an initiator, and now you put an alkene. So this allows you to break this bond, the radical adds to the alkene, so you generate the radical, adds to the alkene, you get a new radical, which now attacks the xanthate, transfers the whole group here, and then you regenerate your radical, and of course it gives you this chain reaction. And now you've created a carbon-carbon bond, and this works even when the alkene is not active, is not activated. Of course, this is a very simplified mechanism. This is the real this is again a simplified mechanism, but it's more detailed than the one I've shown you. I will not go into this. The only thing you have to remember, if I go back to this one here, is that your starting material is xanthate. The product is also xanthate, which means you can start from the product and do a second radical addition, and so on. Okay, so you can do this, and you get products like these. What you can see is an example here. So you make xanthate. So this is the xanthate salt I prepared when I was 16. Of course, it was a different batch that we used when we started this work. And it's very simple to make this, the precursors. And you can see you have an alkene here. You have all these other functional groups. You don't have to worry about them. You can do the addition. You get the xanthate. And of course, now that the xanthate has served its purpose, you can get rid of it by various methods. Here's the method we devised. And you can remove it. And so you have now created this key bond between this xanthate here and this double bond here. So this pluromethylene is an antibacterial, which is used not under this form, but with some modification here for animals, domestic animals. Of course, this is just one xanthate. You can have many, 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 many. We have worked on hundreds of xanthates. We and others now, because now people are using this chemistry. I will not bother you with these details. But let me show you just how you can play with this chemistry. You see, here you have a xanthate. Here you have an alkene. This one is activated, but nevertheless you can do the addition. You get the xanthate. Now you take this with the second alkene, you do a second addition. It's exactly the same reaction. You see, the reagents are the same. And you do the second addition, and you get here, and now you hit it again, slightly different conditions. You force the radical to cyclize, and you make a compound like this. 1, 2, 3 steps. You make a very complex molecular architecture, which has a kind of vague resemblance to colchicine, which also is something that is used in medicine. Now, it turns out that this chemistry has applications for polymers. This is the way you make, classically, one of the ways you make polymers using radical polymerization. For example, polystyrene, which you find every time you buy an iPhone. The white stuff that surrounds the little box, you know, the white material is expanded polystyrene. So polystyrene is when Y is equal to phenyl, okay, this structure here. So you generate a radical. The radical adds from an initiator. It adds to styrene, for example. So Y is phenyl. And then you get a radical which adds to another styrene, which adds to another styrene, and so on. And the radical keeps going until it meets another radical, and they combine. And what you get is the polymer that you have, this white stuff that you have. Of course, you can modify Y. You can have this group here. So now you have acrylate, and you can make polymethyl acrylate. You can make polymethyl methacrylate, which is plexiglass. You can make PVC. If Y is equal to chlorine, you make PVC. So millions of tons are made, of polymers are made this way, and you use them every day. You know, your clothing, your whatever, you know, your car, most things in your home, and so on. So you get a homopolymer. So you say, can't we mix two monomers? You know, put Y and Y prime together. What do you get? Well, what you get is a statistical polymer. So you get maybe two blue ones, one red one, and so on. Maybe two styrenes, one acrylate, and so on. So you can make statistical polymers. So these were easy to make on large scale. What was difficult to make was a block polymer. That is, you make a polymer made of one block of one block of polymer made from one monomer, and the second block made from a second monomer. So you can have different properties here, different properties here. For example, this part could be hydrophobic, does not like water. This part could be hydrophilic and likes water. And so, for example, you can make a super surfactant. You can make things, for example, if you want to stick plastic onto glass, you can have this part which likes the silicone, the silicate part of the glass. This part likes the plastic, and so it acts like a glue between the two. So many applications. But the problem is how to make such things. There were no good methods to do that. And because xanthate, when you do a radical addition, you get also a xanthate. If now, instead of using just one equivalent, for example, of an alkene, and you put styrene in excess, so now your radical R, generated from the xanthate, will add to the styrene. You get the xanthate, but because you can go back to the radical, because this is also a xanthate, you go back to the radical, so you go from here to here. This then will add styrene, transfer the xanthate, add styrene, transfer the xanthate, and so the process keeps going until there is no more styrene. And then the xanthate comes and caps the thing, and you get this polymer. So this polymer is polystyrene, exactly the white stuff that you have in your, but it has this xanthate group at the very end. So you may have 100 units plus this little xanthate at the end. But this allows you to go back to the radical, which means now if you put the second monomer, you can cut this bond and start the process again. And so now you polymerize acrylate. So you add styrene, you get polystyrene, and then add acrylate, and you get polyacrylate. So you get a block made of styrene, a block made of acrylate. And you can modify, so you can make all kinds of combinations. Now this has become industrial. Rhodi block exists, has been made by Rhodia Solvay, and Asteric by Lubrizol. This has become a hot area in polymer chemistry. You can see from the number of publications and number of patents that are related to the subject. So let me just show you pictures, because you can make now blocks like these, 2 blocks, tri-blocks, because you can keep going. You can make structures like star-shaped, comb-shaped, all kinds of things. And so applications, you can see treatments of surfaces, of fibers, of leather. So you can make leather waterproof, for example. Cosmetics, paints, varnishes, adhesives, inks, lubricants, surfactants, detergents, emulsifiers, gelling agents, delivery vectors for drugs, etc., etc., etc. Okay, this is all I wanted to say about our work. Let me now just acknowledge. I will not be able to acknowledge all my collaborators, but I'll just give this citation, this quote in French. So this is the English translation. Capital is accumulated labor. However, since we cannot do everything, there are those who work and those who accumulate. So my students have been doing the work, and I have been accumulating the credit, which is not very fair. Okay, so I have to acknowledge this chemistry cannot be done without the help of students, postdocs, and so on. It's a collaborative work. Their contribution is enormous, and it's not the boss who has to take all the credit. Nevertheless, I would like to mention Beatrice here, who has worked with me for 25 years. She retired almost 2 years ago, and her contribution has been decisive. So I have a great debt to Beatrice. Also a wonderful person, very gifted experimentally, very nice to work with. Advice, as they say in English, advice is cheap. It's cheap because it's mostly useless. Everybody has to learn from his own mistakes. It's very difficult to transfer experience. Of course, the English saying is that you cannot put an old head on young shoulders, simply because young people are not convinced. don't do this. Oh, you know, don't smoke, it could kill you. Oh, no, I'll smoke. But because old people, we have seen people dying of lung cancer. And when you say don't smoke, they say, oh, you know, it's the old guy, what is he saying? And then, you know, 30 years later, they have lung cancer and say, oh, wow, I should have listened to the advice, but it's too late. So it's difficult. So, but this is, I mean, I'm just giving an advice like this, but it could be anything, you know. And not all advice is good, by the way. Don't listen to old guys all the time. Sometimes listen to them. But I will not give you a list of advice. Let me just say that science is a little bit special. In science, science is based on honesty, absolute honesty, scrupulous integrity. You cannot cheat because nature does not cheat. Your opponent, nature, never cheats. So you cannot cheat. And as you can see here from Einstein, you see, no amount of experimentation can prove me right. A single experiment can prove me wrong. So even the great Einstein realized that his theory could be wrong. The other thing science tells you is you have the freedom to doubt. Einstein, when he proposed his, he was not even, he didn't, I don't think he even had a PhD. He had honorary PhDs, but he never submitted a formal PhD. And the establishment thought, who is this guy? You know, we don't want to listen to him. But he was right. And they were all wrong. So the freedom to doubt is key to, this, to science. And as I said, you have to be strictly honest. By the way, Einstein himself did not believe in quantum mechanics. And he thought, you know, God does not play dice. And he proved wrong. But he was wise enough to discuss this, not to impose by his, you know, his authority to say, oh, this is rubbish. You know, he let it go. And of course, but other people sometimes are not so open-minded. Even scientists, not all necessarily all are open-minded. They're like humans. They have all the you know, the strengths and weakness of humans. Facts. Facts are absolutely essential. You have to have correct facts. In life, real life, it's not easy to get facts sometimes. You know, you have lots of disinformation, lots of things which are given which are not necessarily correct, sometimes exaggerated, sometimes completely fabricated. But as you can see here, you see the tragedy of science, the slaying of a beautiful hypothesis by an ugly fact. Very important to get facts right. And of course, mistakes, failures. In life, failures sometimes are depressing. In science, failures oftentimes teach you more than success. If you go back, analyze a failed experiment, you learn from it. In life, you should try to do that. It always improves you to understand why you failed. Even tennis players, they study their matches to avoid making the same mistake. Oh, they say, you know, I should have run more faster here, I should have gone here. In science, you do that all the time. You examine failed experiments and you try and understand them. In real life, this is not done all the time. You find people doing the same mistake over and over again. You know, for instance, Hitler invaded Russia. He did not learn from Napoleon's mistake 1 century before, that you shouldn't invade Russia. He did it, and he paid a heavy price. I mean, he and the, many soldiers. This is not the thing to do. Let me say, we here have this good fortune, to be able to choose what we like to do in life. My parents did not have this choice. I suppose the poor Syrian refugees do not have much choice what to do in life. But, you know, in this audience here, I think most of us have this possibility to choose what we like to do. So if I have to give you an advice, which I gave to my children, I say you only live once. If you have a passion for something, go for it. You may not win a lot of money, you may not earn a lot of money, but you live a happy life because your work becomes your fun. And every day becomes fun day, you know, becomes a day to have fun. So here is a saying by a chemist, and he said, the chemists are a strange class of mortals impelled by an almost insane impulse to seek their pleasures amid smoke and vapor, soot and flame, poisons and poverty. Yet among all these evils, I seem to live so sweetly that I may die if I were to change places with the Persian king. If you can live your passion as a musician, as as an actor, as an artist, as a whatever. Of course, you have to feed your family, so you have to be careful what you do. But still, this is something that if you have the good fortune to do that. I was fortunate, as I told you, to have discovered my passion for chemistry very early. So there was no question for me, what I was going to do later. And my parents had the kindness to let me do what I liked. They never said you have to do this or that. They just said, you want a little lab, here is a room, go and do what you like. Just be careful, which I didn't do very often. I had, these explosions and trying to distill bromine is not the thing to try to do. I was very fortunate to have crossed the path of very exceptional people. Selfdirect Barton, this is a nice picture of him. He had enormous influence on my life. This was another good fortune. This is perhaps the biggest good fortune I had as an adult, after the age 18. Because of him, because I came to France, I met my wife. So here's Sir Derek and his second wife, Christiane, and my wife at our wedding. So it's indirectly because of him that I met my wife. And so we have now 2 children. This is our son, Michael. And here's my wife and myself at INSEAD, when he graduated. This is our daughter, Emily. Now she's married to Quentin. And the full circle has come. This is Gaëtan, who's 1 year old, the same age I had on the picture I showed you at the beginning. Merci.
We have time for a couple of questions, but the microphones are around. But before Professor Zard, can you share with us one of your failures or one of your challenges, and how did you overcome that challenge?
Well, experiment failures. Most of our experiments failed.
Decisions, like one of the big decisions you took in research or life, or you had a good life.
I don't know. Honestly, I don't know, because sorry, I'm looking at the audience, but I made the decision to stay in France, even though at some points like Professor Stoddart, I had some nasty people making life miserable for me. Again, because of jealousy, because of what have you, maybe racism, but I've never seen this, not directly anyway. I don't know. So I had the opportunity to go to the United States at some point. I did not. I stayed in France, even though in France you cannot build a big group. Is this a failure? Would I have done better if I had gone to the United States and had a bigger group? I don't know. So I made a decision, and I can only see the results of my decision. I cannot see what would have happened if I had gone to another country and started, maybe in a more dynamic environment. I'm happily married for 30, so I think I made a good choice with my wife. I'm not sure if the other way is correct. The way she criticizes what I do and what I say is, sometimes I wonder whether she made the right choice. Our children, we have had no problems with our children. They have been wonderful children. Honestly, I cannot say, maybe the decision to leave Lebanon. I needed 1 semester to finish my BSc. We went with almost no plans. We went to France. We didn't know what to do. We spent 1 month turning around, trying to find a place to go. They wouldn't accept me. Should I have stayed in Lebanon? I don't know. But then it turned out to be okay. I don't know these failures, Bilal. I don't know. I don't regret my decisions. Again, because mostly I don't know what would have happened if I have. But I cannot think of a major decision where I had fights. For example, becoming professor at Ecole Polytechnique. The opponents were not playing an honest game.
Oh, that happens everywhere.
Happens everywhere. Fortunately.
Do you want me to start talking about that?
Yeah, fortunately I had the help of many colleagues from abroad. This is something something that you'll find in your work, that not everybody is kind to you, not everybody I mean, sometimes they are nice to you, but they are not necessarily helping you. You have to distinguish between good guys and not the so good guys. And but the real friends are really precious. Having good friends, good mentors, they are really precious, because ultimately when you are down, they are the ones who push you up. Your family and your friends and your very good colleagues. This is key, key, key. I built a group in France where I went against the French system. The French system is a pyramidal system where young people don't have independence. So I only had one collaborator, Beatrice, let's say permanent collaborators, whereas other colleagues had 6, 7. I've refused the system. Beatrice came to work with me. She worked initially in another group, but her former boss retired and came to my group. I said, you want to set up your own group? She said, no, I want to work on your chemistry. And she's the only person I worked with. So I set up at Ecole Polytechnique a system where each young person is independent, which is more the Anglo-Saxon system than the French system. And other colleagues did not like this, but I fought. And I'm stubborn, like you, Bilal. I'm stubborn. You know, and fortunately...
You don't look at them.
Yeah, ask my wife. You know? Yeah, she says, I'm tête de mule, you know.
Any questions from the audience? Okay, we got to date. Before we thank Professor Zard, we have a tradition to hand the speaker the poster. So I asked my team to join me here. Let's thank Professor Zard, and then we take a group picture with Professor Zard. My team, join me here, please. We usually give the speaker
that's
a
lovely.
copy of the poster that we take a picture with the
Okay,
speaker.
thank you. So let's do it the way you want.
Yeah, thank you.
Thank you.
Thank you, everyone.
so
Thank
much,
you once
Professor
again.
Zard.